Good evening, everyone, and welcome to the Project Euler series. For those of you guys who emailed me or commented on the video and asked me to continue the series, I will be doing so. And today we're going to be solving problem 33. It states that we're given a number like 49 divided by 98, and as an inexperienced mathematician, we're trying to simplify it incorrectly. So what we do is we chop off the 9's, right, and we get something like 4 divided by 8, which is actually correct, right? And we obtain that by actually canceling out the 9's. We should consider fractions like 30 divided by 50, right, which is going to equal to 3 divided by 5 to be trivial examples. There are exactly 4 non-trivial examples of this type of fractions, less than 1 in value, and containing 2 digits in the numerator and denominator. If the product of these 4 fractions is given in its lowest common term, find the value of its denominator. So what do we know about this problem? Well, we know that the numerator and denominator are going to have 2 digits each, right? Also, we know that the numerator has to be less than the denominator, or else we will get a value greater than 1, and we need something less than 1. Also, we need to find the lowest common term, right, which is going to be the value of the denominator. So we need to use GCD for this, and we can use the Lucid algorithm for that. All right. So is there a way that we can solve this problem mathematically? Well, it's product Euler, so there is. However, that solution is a lot more complicated, even though it's less code, and it requires a bit of math. So what I wanted to do was provide an alternate solution that's quite simpler, and you guys can actually visualize it, versus something that would require me to go through a lot of mathematical formulas, and you might not still get it, right? So let's get started. So what I've done, like always, is create a Java class. I've called it canceling fractions. So what do we need first? Well, we need that GCD. So let's go ahead and just create a GCD. I'll make everything static, right? Let me do double here. Just got a GCD here, and let's do double A, double B, and we can do this recursively. So just return A equal to 0. We want to return B. Else we want to recalculate that GCD, so we're going to say B mod A and A, and there we go. So this is pretty simple. I'm not going to go into the workings of the GCD because it's not that big of a problem for this specific problem, right? So what we need to do is we need to work on the second part of this. So what happens if we have a number like, let's say 22 over 22, or let's say we have 30 divided by 50. Well, there's something that correlates with this problem, is that if we remove the 0, right, okay, then we end up with a value that is still gonna give us the exact same answer as a reduced form. So we can optimize it by skipping those, right? So we can optimize it by skipping those values. The reason why it said that 30 divided by 50 is trivial, it means that we can kind of eliminate those, and it won't still affect the solution for the problem. So let's do this. Let's try to erase those. So we're going to create a static, a boolean, and this one we're going to try to simplify the digit. All right, so we're going to simplify the digit. It's going to be, let's get a double A and a double B. All right. So what I want to do is I want to use a string builder, and you guys will see the reason why, because we can kind of use this to eliminate string builder, and let's do double dot toString and pass in A, and let's copy this for B. So Control C, Control Z, and Control V. All right, and let's change this to, say, J, and change this to B, right? So what we want to do is we want to return, right, let's do I dot charat 0, right, is equal to j dot char at 0. Or if the two first numbers match or the last two numbers match, then we want to ignore it. So we're going to say I dot char at 1 is equal to char j dot char at 1. All right, and we're going to use this later on when we are working on the final solution. Next, what do we want to do? Well, we know that if we have a number like 50, right, for example, like 30 and 50, then if we take 30 divided by 50, right, and we take 3 divided by 5, then we should get the exact same solution. So why don't we use the why don't we cancel, right, the numbers, the zeros here, and actually just return 3 divided by 5, right? And then we can calculate, we can mash that answer to the original calculations for the numerator divided by the denominator to the reduced form of it. So let's go ahead and do that. So let's create a private static double, and let's call this one remove. Let's call this sim, right? And this is going to be, let's do double A and double B. All right, and I guess we could just kind of copy this here, kind of save time. So Control C and Control V. All right, so how are we going to do this? Well, we know there are going to be 2 values in the top and 2 values in the bottom part. So what we can do is that if the numbers, right, are, if the index zeros for both I and j are 0 and they're equal to each other, then we can cancel those. Or if they're in the one spot, we can cancel those. We can also cancel from the diagonals, right, from right to left and from left to right. All right, so what we can do is we say if, right, I dot char at 0, right, is equal to j dot char at 0, then we want to do some few things. We want to say I dot delete char at 0, right, and j dot delete char at 0. And then we want to reduce that, we want to return that reduced form, so we're going to return double dot parse double, and we're going to pass in the numerator, which is going to be I. So I dot toString divided by the denominator, which is going to be double dot parse double, and we're going to do j dot toString. All right, I hope this makes sense. And now we want to do it for the values in the second spot. So I'm going to copy this and we just paste it here, and here we could just, let's just do this for the diagonal. So we're going to say 0 and 1, right, and we can change j here to 1. This is if the first number in the I, right, matches with the last number in j. And we can do the exact same thing as well, just reverse the order. And here we're going to do 1 for if the second number in j matches to the first number in I matches to the first number in j. So here we're going to change this to 1. And then we have the last case for 1 and 1 if the ones match, right? So we're going to change this to 1s and 1. All right. I'm actually putting all of this if statements here for completion's sake, okay? Because eventually, if you decide you're gonna run this code and maybe output every statement out, you realize that for this problem and the way that I kind of wrote the upper method, that you don't quite need every single check like this. It will work without certain checks, and I will leave that up to you to actually find out and see which checks you actually need and which checks you don't need. But by putting it this way, you can actually see what I'm trying to do with the cancellations, so you can create a better algorithm to solve this, okay? But I'm putting in the checks there just for completion's sake. You don't need every single one of them. And if any of these cases don't pass, then we know that the number is actually bigger than 1, so we could just return 1. Okay, so return random 0, and we're good. Now we need to go ahead and actually implement our cancel fractions. Okay, so let's make this double, and I'll just call this cn frac for cancel fraction. And you can pass in an upper limit here, which is going to be 99. I think hard coding it might just be as good. So what do we need? We need some variables. We need a double for the let's do the numerator. It's going to equal to 1, and we need another variable for the denominator. So we're going to do denominator is going to equal to 1. Now I'm going to say for double, why this happens, num is going to equal to 10. All right, because that's the first 2-digit number that we have. And then we're going to do num, right, is less than or equal to 99. So I downloaded this material theme, and apparently it's messing up with my symbols, so kind of bear in mind with that. But this is less than or equal to. All right, and we need 1 for the denominator, so I'm going to say double dnum, right, is going to equal to num plus 1. Like I said, the reason why it's num plus 1 is because the numerator has to be bigger than the denominator, or the value that you're most likely to get is going to be greater than 1. And so what we want to do next, we want to say that the denominator, right, is less than or equal to 99, and you're going to do denum plus plus. All right, so now we need to go ahead and do a few things. We need to do our calculations. Okay, so what do we need first? Well, we have this sim function here that kind of checks for values that we can kind of ignore, right? So let's use that here. So what we're going to do, we're going to say if sim digit, and we're going to take in the num and the denum, right? If that matches that case, then we just want to continue. We don't want to do anything. All right, we want to skip it. So we get a little bit of optimization there. Next, we want to get the GCD. So just create a double here, and we can call this one divisor or factor, however you want, and let's pass in GCD here, and we're gonna do one for, we're gonna pass in num and denum. Okay, next what we want to do is we want to get that reduced form, and that reduced form is going to come from our remove simplify here. Okay, so remember that we had 50, 30 and 50, then we want to remove the last zeros, right? So eventually we're just going to get 3 and 5. So we take 3 divided by 5, and then it's going to return that answer here. So we can call this one reduced. Okay, so reduced is going to equal to all right, remove sim, and then we're going to pass in the num and the denum. So remember that the num has to go first because I set it as I, and if you try to divide it in the wrong order, it won't work. So what do we want to do next? Well, we want to keep that original value. So I want to get that original value. All right, and the original value would be the 30 divided by the 50. So let's call this one original, or origin. It's going to equal to, right, num, right, divided by denum. So if we divide 30, right, divided by 50, we should get the same result as 3 divided by 5. I'm going to say if, right, reduce is equal to origin, then we've matched one of the cases for this problem. So why the hell do I even have the factor there? Well, the reason why I have the factor there is because I want to reduce, I want that reduced form. Okay, I know maybe you don't really need it, but I wanted that reduced form so that I could simplify the way that the GCD is going to work. Why did I do that? Well, it's recursive. Okay, and I was thinking, what happens if the value is way too big, right? And we cannot recurse over that, and it goes to infinity. Then this would have been for nothing. So anyway, what do we need here? So we need the numerator, right? That's gonna times equal to, and we need the numerator divided by the factor, so we can reduce that. We can get the factors in its reduced form, and the denominator is going to times equal denum, right, divided by factor. And now once we're done with this, we just need to get that denominator in its lowest common form. So what we're going to do is return denominator, right, divided by the GCD of the numerator and the denominator. Okay. All right, and we're done with this. And so let's just go ahead and test this out. So I'm going to pass in the system, public static void function for main. And let's just bring this out, and I'll call the cancel frag. Okay, and let's run this. And you should get 100 for the final result. So why is that? Well, because I reduced everything right here, you're only gonna get 2 for the numerator, and you're gonna get 200 for the denominator. Well, if you run the GCD for the 2 and the 200, you're gonna get 2, right, for the greatest common divisor. Well, 200 divided by 2 is gonna give you 100, and this solves the problem. So I hope you guys actually get what I was going for. And what was I trying to tell you guys here? Well, let me go ahead and cancel this out. Okay, let me kind of uncomment this, and let me run this again and see if this really changes the solution. Well, it didn't change the solution, right? So I was saying that some of the checks in this process here are not quite needed. Okay, the reason is because of the way that I wrote the functions, right? And the reason why I have it in here is because I want to show you guys a visual way of actually seeing this problem, so that you guys can kind of think about it and say, well, can I optimize this even further? So let's go ahead and look at the runtime for this. All right, obviously if you use the math version for this, the runtime is actually going to be 0. All right, that's how good the mathematical one is. So let's check out the runtime for this, because I haven't checked it out myself. But it shouldn't be that bad. It shouldn't be something where it should go over 1 second. All right, I think it should be much less than that. Let's do system output line. Let's cast the first one. Let's do n minus start. Right, and then we're going to divide this by 1000 so we can get it in seconds. And if we run this, you can see that we get the runtime is pretty good. It's less than a second. Okay, so this is not a bad runtime. I think that doing it this way is actually a lot more clever, right? If you guys actually have any questions about this, if anything you guys are unsure about, please leave a comment so that I can respond to it. If you guys like a tutorial, give me a thumb up and a like. If you haven't subscribed to my channel yet, please do so. I will see you guys on the next Project Euler tutorial. Have a good day. Bye bye.